Good evening. Settle in, get comfortable, and prepare for a journey into the deepest corners of our cosmos. Imagine a star. It's so far away that its light has been traveling toward us for almost 1,500 years. Like millions of other stars, it should shine with a steady, predictable brilliance. But this star behaves differently. It disappears. Its brightness drops suddenly, chaotically, and by a massive amount, as if something gigantic and dark were periodically eclipsing it. What is this? A data error? An unknown natural phenomenon? Or something artificial? Tonight we are traveling to KIC 846282, better known as Tabby's star. I promise you that by the end of this presentation, you will understand why this distant pinprick of light forced the entire scientific community to hold its breath and seriously discuss the possibility of alien megastructures. This story sounds like science fiction, but it is happening right now, in reality. Let's delve into the greatest cosmic mystery of the 21st century. To truly grasp the strangeness of what happened, we need to take a step back to the year 2009. That was when NASA launched the Kepler space telescope. Its mission was simple yet incredibly ambitious: to find exoplanets, planets outside our own solar system. Kepler couldn't see these planets directly. Instead, it used what's known as the transit method. Imagine you are looking at a light bulb. If a tiny fly passes in front of it, the light will dim slightly for an instant. Kepler did the same thing, but with hundreds of thousands of stars simultaneously. For years, it stared unblinkingly at the same patch of sky in the Cygnus constellation, measuring the slightest fluctuations in stellar brightness. When a planet passes in front of its star, it blocks a tiny fraction of that light, and the telescope records this predictable, periodic dip in brightness. Thousands of new worlds were discovered this way. However, Kepler gathered so much data that scientists simply couldn't process it all. This led to the launch of a citizen science project called Planet Hunters. Anyone could go online, look at the star brightness graphs, the light curves, and help find those characteristic dips that signaled the presence of a planet. And there, amidst hundreds of thousands of normal, predictable graphs, volunteers stumbled upon something impossible: a star whose brightness curve looked like nothing anyone had ever seen before. This was our subject, Tabby's star. Let's dive right into the moment when a routine evening for the volunteers of the Planet Hunters project turned into the opening chapter of one of the greatest astronomical mysteries of our time. Imagine the software interface. Thousands of graphs scroll past. The x-axis tracks time, the y-axis tracks the star's brightness. Most of them are just straight lines with a little noise. Occasionally, you see a neat, symmetrical U-shaped dip that repeats at regular intervals. That's the classic signature of an orbiting planet. But the light curve for the star KIC 84628252 was different. It was wild, it was chaotic. It showed messy, asymmetric drops in brightness that occurred completely without periodicity. The most striking thing was the depth of these dips. When a Jupiter-sized planet, the largest giant in our system, passes in front of a Sun-sized star, it blocks only about 1% of the light. It's barely noticeable. But Tabby's star dropped by 15% and, in one instance, even 22%. To put that scale into perspective, to block 22% of a Sun-like star's light, the object would have to be 1,000 times larger in surface area than Jupiter. This couldn't be a planet. And it definitely wasn't a companion star, which would have been easily spotted using other methods. The volunteers started discussing this strange object on forums, drawing the attention of professional astronomers. One of them was Tabitha Boyajian, a postdoctoral researcher from Yale University. It is in her honor that the star would later be nicknamed Tabby's Star. At first, like many others, she was skeptical. It was probably a data error, an instrumental artifact. The Kepler telescope is an incredibly complex instrument, and glitches happen. But after meticulously checking all the data, re-verifying the calibration, and analyzing the telescope's performance, the conclusion was singular. The data was sound. The star truly was behaving this strangely. It was not a mistake, it was reality. And this reality simply did not fit any known astrophysical model. The scientific community was stumped. Something enormous, dark and irregularly shaped, was orbiting a distant star, and no one had the slightest clue what it could be. This was the beginning of a long and fascinating investigation. Once the initial shock of confirming the data subsided, scientists started sifting through potential natural explanations. The first thing that springs to mind is a protoplanetary disk. Perhaps Tabby's star is very young, still swaddled in the remnants of gas and dust, from which planets are only just beginning to form. In these disks, dense clumps of material could be orbiting the star, periodically causing the observed dips in brightness. This hypothesis seems logical, but it faces one fatal flaw. Young stars surrounded by dust disks emit copious amounts of infrared radiation. The dust absorbs the star's light, heats up, and then re-emits that energy at longer wavelengths. Think of hot asphalt on a summer day. You don't see the sunlight it absorbed, but you certainly feel the heat it radiates. Astronomers aimed infrared telescopes like Spitzer and WISE at Tabby's star and found no sign of excess infrared emission. The star was completely clean in that spectrum. This lack of IR energy meant there was no significant amount of warm dust orbiting the star. The young protoplanetary disk hypothesis was ruled out. Okay, if it wasn't a disk, perhaps it was the aftermath of a recent cosmic catastrophe. For instance, two planets colliding. Such an event would launch a massive, irregular cloud of debris and dust into orbit, which could then block the light. This idea was also attractive as it explained both the vast size and the irregular shape of the obscuring material. However, this theory also proved disappointing. Calculations showed that such a massive cloud of debris wouldn't remain stable for long. The star's gravity and the pressure of its light would quickly disperse it. Furthermore, the fine dust inevitably produced by such a collision would, once again, generate the infrared excess that we were not seeing. To account for the 4 years of continuous observations by Kepler, this would require an incredibly recent and monumental collision, the remnants of which should have been clearly visible, but they weren't. Every attempt to find a simple, natural explanation ran into insurmountable contradictions with the observed data. The mystery deepened. The material orbiting the star was cold, eliminating most dust-based scenarios, yet it covered a gigantic area. Scientists were running out of conventional ideas, and it was at this precise moment that the boldest and most provocative hypothesis of them all finally took center stage. When standard astrophysical models hit a dead end, it often pays to think outside the box. That's precisely the approach taken by astronomer Jason Wright from Penn State University. He and his colleagues were analyzing Kepler data with a totally different goal in mind. They were hunting for technosignatures. In other words, evidence of advanced extraterrestrial activity. When they examined the light curve of Tabby's star, they realized it bore a striking resemblance to what you might expect from an alien megastructure. Thus, the star's most famous theory was born. The core idea suggests that any highly advanced civilization, on reaching a certain technological threshold, will inevitably face an energy crisis. Their power demands would grow exponentially, making the energy output of their home planet insufficient. The logical solution would be to start harvesting their star's energy directly. As far back as the 1960s, physicist Freeman Dyson proposed that such a civilization might construct a colossal structure around their star to capture most of its radiation. This could manifest as a solid shell known as a Dyson Sphere, or, more realistically from an engineering standpoint, a massive collection of individual satellites and collectors orbiting in various paths, known as a Dyson swarm. Such a swarm, consisting of thousands of giant panels, could perfectly explain the bizarre dips in Tabby's star's brightness. Large, individual structures or dense clusters of collectors passing in front of the star would generate those deep, asymmetrical drops in light. The chaotic, non-periodic nature of these dips would be a natural consequence of the complex orbital dynamics of countless separate objects. This hypothesis, while undeniably fantastic, held a crucial advantage. It provided an elegant explanation for the light curve's key features, where natural explanations had completely failed. Jason Wright published a paper cautiously suggesting that Tabby's star should be considered a premier candidate in the search for extraterrestrial intelligence. The news detonated like a bomb. Headlines across newspapers and news sites worldwide screamed about the alien star. The story quickly transcended the scientific community, capturing the imagination of millions. It was one of those rare moments when respected, serious scientists were openly and genuinely discussing the possible detection of alien technology. The alien megastructure hypothesis was certainly thrilling, but in science, extraordinary claims require extraordinary evidence. The first crucial step was to rigorously test the theory. The main argument against it was the same one used against the protoplanetary disk hypothesis, a critical lack of infrared radiation. According to the laws of thermodynamics, any structure built to harvest energy cannot utilize 100% of that energy. Some portion must inevitably be lost as waste heat. A massive Dyson swarm, absorbing up to 20% of the star's light, would heat up drastically, becoming an immensely powerful source of infrared radiation. It should, in fact, glow brighter in the infrared spectrum than the star itself. However, as we already know, dedicated observations revealed no such thing. This represented a crushing blow to the theory. Proponents of the hypothesis scrambled for workarounds. They suggested, for example, that the civilization might have found ways to shed excess heat through unknown means, potentially violating the known laws of physics. However, this quickly pushed the discussion out of the realm of science and into pure speculation. Another suggestion was that the megastructure was still under construction, with most of its elements being extremely cold and therefore not radiating heat. Yet, even this didn't fully resolve the underlying problem. This is when the SETI Institute, the organization dedicated to the search for extraterrestrial intelligence, got involved. If a highly advanced civilization truly existed around Tabby's star, they would likely be using radio communication. Scientists pointed the most powerful radio telescopes, such as the Green Bank Telescope and the Allen Telescope Array, toward the star and began listening for artificial signals. They scanned millions of radio channels, hoping to pick up anything, be it a deliberate transmission or incidental leakage from their local broadcasts. The result, however, was predictable: absolute silence. No signals distinguishable from natural cosmic background noise were detected. Of course, this doesn't conclusively prove the absence of a civilization. They might utilize other communication methods such as lasers, or they could simply choose to be silent. But the combined lack of both a thermal and a radio signature made the megastructure hypothesis extremely improbable. It remained a beautiful and imagination-stirring idea, but the scientific data spoke volumes against it. The investigation had to return to searching for natural, if highly exotic, explanations. Once the initial excitement surrounding aliens began to die down, astronomers reverted to more grounded, though no less ambitious ideas. One of the leading natural hypotheses centered on a massive comet swarm. Comets are essentially giant dirty snowballs made up of ice, rock, and dust. As they approach a star, the heat causes the ice to sublimate, turn directly to gas, creating an enormous cloud of gas and dust around the comet, known as the coma, and the famous tail. Crucially, comets and their tails are composed primarily of cold material that doesn't strongly radiate heat in the infrared spectrum. This neatly solves the central problem that plagued other theories. So, what if Tabby's star wasn't orbited by just one or two comets, but by a gargantuan swarm of thousands, maybe even millions? If such a dense group passed between us and the star, it absolutely could block a significant percentage of light. And since comets are irregularly shaped and surrounded by gaseous clouds, this could easily explain the asymmetrical and chaotic profile of the dips in brightness. This hypothesis, proposed by Tabitha Boyajian herself and her team in their very first paper, looked highly plausible. But it also had its complications. First, scale. To account for a 22% drop in brightness, the required comet swarm would have to be truly colossal. It would need to be something akin to an entire Oort cloud passing through the system's inner orbits, only vastly denser. Where could such a swarm originate? Perhaps a gravitational perturbation from a nearby passing star knocked an enormous number of comets out of their distant orbits, sending them plummeting toward the center of the system. While theoretically possible, such an event would be extremely rare. Second, the synchronization problem. To create one massive dip, all these comets would need to be traveling on very similar, elongated elliptical orbits and arrive at the star around the same time. Maintaining such a dense group for long is incredibly difficult. Gravitational interactions would quickly scatter them onto wildly different trajectories. Despite these challenges, the comet hypothesis remained one of the most popular for a long time. It elegantly explained both the lack of infrared heat and the irregular shape of the dimming events. While it required some unlikely coincidences, improbable things occasionally happen in the vastness of space. Scientists continued monitoring the star, hoping to find new data that could either confirm or finally refute this elegant, yet still incomplete theory. Just as scientists were busy debating comets and megastructures, new and even stranger data emerged. Astronomer Bradley Schaefer decided to check if Tabby's star had behaved strangely in the past as well. He turned to the Harvard Observatory archives, which house glass photographic plates containing images of the night sky dating back to the late 19th century. Analyzing this old, non-digital data was painstaking work, but what he discovered plunged everyone into a new state of shock. The analysis showed that over the span of a century, specifically from 1890 to 1989, Tabby's star had gradually and consistently been losing its brightness. The total drop amounted to about 20%. This was something completely new. Short, sudden dips in brightness which Kepler had recorded were one thing. A slow, century-long fading was quite another. This discovery cast doubt on virtually every existing theory. A giant swarm of comets couldn't account for such a long-term, gradual change. Comets would either pass the star or fall into it. They couldn't possibly hover in orbit for 100 years, gradually blocking more and more light. The planetary collision hypothesis also failed. The debris cloud would have long since dissipated. Even the alien megastructure theory ran into trouble. It would require assuming that a civilization began massive construction a century ago, and that we are now observing them gradually covering their star with new panels. That seemed like too much of a coincidence. Schaefer's work immediately sparked vigorous debate within the scientific community. Some critics pointed out that analyzing old photographic plates is inherently complex, and that century-long changes in telescopes, emulsions, and processing methods could create a false effect of gradual dimming. However, subsequent, more precise analyses of digital data from other 21st century telescopes confirmed the finding. The star truly is continuing to fade. On top of that secular trend, the star lost an additional 3% of brightness during Kepler's 4 years of observation. So the mystery was now twofold. We have rapid, deep, and chaotic dips in brightness, and we have a slow, nearly linear decline in luminosity spanning at least a century. Any successful theory now had to account for both phenomena simultaneously. This made the task virtually impossible and forced scientists to search for even more exotic and non-standard ideas. Once the data confirmed the long-term or secular dimming, researchers shifted their focus to dust, not the kind orbiting the star, but the kind found in the space between us and the star. The interstellar dust hypothesis was actually one of the initial ideas, but it was quickly dismissed. The reason? A standard, uniform cloud of interstellar dust couldn't possibly account for the rapid and dramatic dips observed by Kepler. Such a cloud would be massive and diffuse, and its transit across the star would only cause a very gradual, slow change in brightness. However, the new data forced astronomers to revisit this hypothesis and completely re-evaluate it. What if the dust wasn't typical? What if it possessed a complex, clumpy, non-uniform structure? Imagine it not as a uniform fog, but as something resembling Swiss cheese or a sponge, full of dense knots and empty gaps. If such a non-homogeneous cloud were drifting through the space between us and Tabby's star, its movement could elegantly account for both types of dimming events. The slow, secular decline in brightness would be the result of our entire solar system and Tabby's star gradually moving into a denser region of the cloud. The fast, sharp dips, however, would be caused by individual, very dense and compact clumps within that cloud passing directly across the star's face. This hypothesis, known as the clumpy interstellar dust model, elegantly resolved several issues. Critically, it didn't require any material to be orbiting the star itself, which immediately solved the puzzle of the missing infrared radiation, as dust far out in interstellar space is extremely cold. Moreover, it could explain both the long-term trend and the short-term dips. But like every other theory proposed, it wasn't without its weaknesses. First, it required an extremely fortunate coincidence that such an unusual, complexly structured dust cloud just happened to align precisely with our line of sight to this specific star. Second, the velocity of the cloud had to be very precisely fine-tuned to match the observed dimming pattern. Third, the actual nature of the dust remained a question mark. Standard interstellar dust is composed of extremely fine particles similar in size to smoke. This kind of dust preferentially absorbs and scatters blue light more than red light. Consequently, as the star dimmed, it should simultaneously appear to become redder, a well-known phenomenon astronomers call interstellar reddening. Initial color analyses of Tabby's star during the deep dips did not provide a clear, unambiguous answer, leaving the hypothesis hanging in the balance. While it was one of the strongest candidates, it was still missing that critical, conclusive proof. While theorists puzzled over the data, observers weren't idle. Once the Kepler mission wrapped up, Tabby's star drifted out of its field of view. A concerning lull followed, leaving astronomers worried. What if the main event had already passed? Had we missed our chance to solve the mystery? Tabitha Boyajian and her colleagues knew they couldn't afford to lose sight of this object. They launched a campaign on the crowdfunding platform Kickstarter to raise money for continuous monitoring using ground-based telescopes. The campaign was a resounding success, raising over $100,000. This funding secured dedicated time on the global network of telescopes known as the Las Cumbres Observatory. Now, whenever the star began to dim again, astronomers worldwide would be ready to instantly point their instruments at it and study the event in fine detail. And their patience paid off. In May 2017, after a nearly 2-year hiatus, Tabby's star started blinking again. A new, long-anticipated dip in brightness had begun. Astronomers nicknamed this event LC, after the abbreviation LC, standing for light curve. For the first time, scientists had the opportunity to observe a dimming event in real time, utilizing the full arsenal of modern astronomy. Telescopes across the globe focused on this single point in the Cygnus constellation. Researchers measured not just the overall brightness, but the brightness across different color filters, blue, red, and infrared. And these observations yielded crucial results. It was definitively established that the star did not dim equally across all colors. Blue light was blocked significantly more than red light. The star was literally reddening during the blackout. This effect, as we previously discussed, is the classic signature of dust. This was a vital discovery. It practically ruled out the hypothesis of an alien megastructure entirely. Any solid, opaque object, whether a solar panel array or a spacecraft, would block all colors equally. Comets, composed mostly of water ice, couldn't produce such a strong color imbalance either. The data clearly indicated that the culprit was a cloud of dust, comprised of particles smaller than a micron. This represented a huge leap forward. The mystery wasn't solved yet, but the circle of suspects had dramatically narrowed. The main question was no longer, what is it? But rather, where did this dust come from and why is it behaving so strangely? Okay, so we know it's dust, but what kind of dust is it? And where is it located? New data concerning the star's reddening during the dimming events allowed scientists not only to confirm the dusty nature of the object, but also to place specific constraints on its characteristics. The fact that blue light is blocked more effectively than red light suggests that the dust particles must be extremely small, less than a micron in diameter. This is far smaller than, say, a grain of sand. It's more akin to particles of smoke or soot. Furthermore, analyzing the shape of the light curve during the LC event and subsequent dimmings revealed that the dust cloud is not uniform or solid. Instead, it has a complex, fibrous structure. This observation reinforced the idea that the obscuring material is clumpy or patchy in nature. A clearer picture is now emerging. Surrounding Tabby's star, or along our line of sight to it, is an enormous, sparse cloud of incredibly fine dust, characterized by a non-uniform, fragmented structure. This model is commonly called circumstellar dust. Crucially, it posits that the dust is orbiting the star rather than floating in interstellar space. But this brings us back to an older problem. Why isn't this dust heating up and glowing brightly in the infrared spectrum? The answer might lie in geometry. If the dust isn't orbiting in a perfect circle, but rather in a highly elongated elliptical path, it would spend most of its time very far from the star, where temperatures are low. It only swings close to the star for a short period, causing the dimming event, before retreating again into the cold depths of space. Crucially, during that brief flyby, it doesn't have time to heat up significantly. This eccentric orbit dust model has become a leading hypothesis. It elegantly explains the nature of the dimmings, the dust, their irregularity, the stretched orbit, and the lack of thermal emission. The dust is mostly cold. However, it leaves the central question unanswered. Where did this dust come from? What mechanism could create such a massive cloud and launch it into such a strange orbit? Plausible scenarios include the tidal disruption of a planet or an asteroid group by the star's gravity, or perhaps the aftermath of a catastrophic collision between two bodies in the system. Yet none of these scenarios fully account for all the observed details, including the long-term secular decrease in brightness. The mystery of Tabby's star has transformed It is no longer a question of what is it, but rather what is the source of this dust? And that question has proven to be equally complex. Let's dive deeper into one of the most intriguing scenarios that could explain the origin of this enigmatic dust, the destruction of exocomets. We've discussed the comet swarm hypothesis, but that ran into a scale problem. However, what if we're not seeing a simple swarm, but rather the remnants of one or several giant comets that approached the star too closely and were subsequently ripped apart by its gravity? This phenomenon, known as tidal disruption, is well known to astronomers. We observed it firsthand in our own solar system when comet Shoemaker-Levy 9 was torn to pieces by Jupiter's gravity in 1992, with the fragments later slamming into the gas giant. If a similar event occurred near Tabby's star, it would create an elongated cloud of debris, ice, and dust orbiting along a highly eccentric path. Such a cloud, when passing in front of the star, could easily cause the observed dimming events. This model offers several key advantages. First, it naturally accounts for the material's highly elongated orbit, which simultaneously resolves the problem of the lack of excess infrared radiation. Second, it can explain the complex structure of the light curves, as different fragments of the destroyed comet would block the light in unique patterns. Third, it explains the presence of fine dust, which would be created when the ice sublimates under the stellar radiation. But this hypothesis also has its drawbacks. The main problem is the long-term, century-long dimming. It's difficult to imagine how a single tidal disruption event could lead to a steady, continuous drop in brightness over a period of 100 years. Over time, the debris cloud should either fall into the star, be ejected from the system entirely, or distribute itself more uniformly along the orbit, not continue to block progressively more light. Some scientists suggest that we might be observing not the consequence of one event, but rather a series of such disruptions, or perhaps a very complex cascading process where the fragments of one comet collide with each other, generating new waves of dust. While this makes the model more complicated, it also makes it more flexible. We might be witnessing a unique, intense period in this star system's life, a heavy bombardment of the central star by the icy remnants from its distant outskirts. It's a beautiful and dynamic picture, yet it remains a hypothesis that requires further confirmation. Future observations focused on the chemical composition of the dust during upcoming dimming events could shed light on this issue. If we were to detect traces of water or other volatile compounds in the star's spectrum, that would be strong evidence supporting the cometary nature of the mysterious material. Let's return to the idea of the dust cloud and approach it from a completely different angle. What if this material didn't come from outside, like a swarm of comets, but was instead generated internally, born from a catastrophic event right there in the system? Imagine two celestial bodies, maybe two planets or a planet, and a massive asteroid, which had maintained stable orbits for millions of years. But then, due to gravitational perturbations, possibly caused by a distant, unseen companion star, their paths diverged and crossed. The result? A cataclysmic collision. The energy released by such an impact would be colossal, easily capable of completely destroying both objects and ejecting a tremendous amount of debris into orbit. Everything from large asteroids down to the finest dust. This cloud of orbiting debris would be more than enough to account for the observed dimmings. Like the cometary model, this impact theory has several compelling strengths. First, it easily accounts for the sheer volume of material needed to block 22% of the starlight. The destruction of just two Earth-sized planets would generate more than enough debris. It also explains the irregular shape of the dimmings, since the resulting debris cloud would be highly non-uniform from the start. However, this is where we run into familiar issues once again. The first is heat. Immediately following the crash, the material would have been incredibly hot, creating a powerful infrared signature that would slowly fade over time. We simply don't see that signal today. We could circumvent this by assuming the collision happened far in the past, allowing the debris to cool down completely. But this introduces our second major problem, dynamics. Over time, stellar gravity and mutual collisions would grind the large fragments into ever finer dust. Then the pressure of starlight and the stellar wind would gradually sweep this fine dust out of the system entirely. The cloud should have long since dissipated. For the cloud to persist long enough to cause the events we observe today, the required initial conditions would have to be extremely specific. Furthermore, just like the comet hypothesis, the planetary collision scenario fails to adequately explain the long-term secular dimming of the star. It accounts for a single, massive input of dust, but not its gradual accumulation in our line of sight over a 100-year period. Perhaps we aren't looking at one massive impact, but a series of smaller collisions within a dense asteroid belt, a kind of celestial chain reaction. But that only complicates the model further, making the hypothesis significantly less probable. The planetary catastrophe scenario remains a plausible explanation. However, it is far from a perfect solution. Like all the others, it addresses one part of the mystery, but leaves a crucial piece of the puzzle completely unanswered. Let's turn our attention to another rather exotic, yet physically plausible idea. What if the anomaly isn't caused by something orbiting the star, but by the star itself? Tabby's star is an F-type star, meaning it's a little bigger, hotter, and brighter than our own Sun. Usually, these types of stars are quite stable, but what if an unknown process happening deep inside the star, or on its surface, is causing these bizarre changes in brightness? For example, some variable stars show complex activity cycles, but none of the known types match Tabby's star's behavior. Its dimmings are simply too deep and too irregular. Astronomer Brian Metzger and his colleagues proposed an intriguing model involving the star ingesting a planet. Imagine a planet in this system on a very close orbit. It gradually spiraled inward and was finally consumed by the star. This event might have temporarily increased the star's brightness, and then, as the planetary material settled and mixed inside the star, its luminosity might have started to gradually decline. In theory, this could explain the long-term secular dimming, but what about the rapid, short dips? The model suggests that some of the consumed planet's material could have been ejected back into orbit, forming a temporary cloud of dust and gas. However, this scenario requires a very precise alignment of numerous factors and still doesn't fully explain all the intricacies of the light curve. Another internal hypothesis involves magnetic fields. Our own Sun has activity cycles driven by its magnetic field, which cause sunspots. Sunspots are cooler, darker regions on the surface, and when there are many of them, the Sun's overall brightness slightly drops. What if Tabby's star is undergoing some sort of extreme magnetic process, creating gigantic star spots that cover up to 20% of its surface? This would explain the drop in brightness without needing any external object. But this idea faces serious difficulties. First, such gigantic spots have never been observed on stars of this type. Second, spots are usually linked to a strong magnetic field and X-ray activity, neither of which is observed around Tabby's star. Third, spots rotate with the star, which should create periodic signals, yet the dimmings observed at Tabby's star are chaotic. Hypotheses related to internal stellar processes currently appear less likely than theories involving circumstellar material, but we cannot dismiss them entirely. Perhaps we are witnessing an entirely new, previously unknown type of stellar variability. Among the myriad of theories proposed, some sit right on the border between natural and artificial explanations. One such concept involves stellar engineering used not for harvesting energy, but for entirely different goals. For instance, waste disposal. A highly developed civilization, one that has existed for millions of years, will inevitably face massive waste accumulation problems, including mountains of radioactive material. One of the most effective, albeit technologically challenging, ways to permanently eliminate this waste would be to simply jettison it directly into their star. This would require specialized containers or transport vessels designed to deliver the waste to the stellar surface. If such a civilization systematically engages in this stellar recycling, we might observe these transit streams passing in front of the star. This hypothesis could easily explain some of the observed oddities. For example, if the container ships varied in size and followed different, irregular trajectories, it would perfectly account for the inconsistent depths and timing of the observed dimming events. However, this idea, much like the Dyson Sphere hypothesis, runs straight into the problem of missing techno-signatures. We detect no radio transmissions, nor do we see any thermal exhaust trails from the engines of these hypothetical vessels. Furthermore, the sheer scale required is simply mind-boggling. To block 22% of a star's light, you would need a fleet of colossal ships comparable in size to small planets. Why build such enormous constructions merely to transport trash? It seems like engineering overkill. Another variation on a purpose-built megastructure involves creating shade rather than collecting energy. Perhaps the civilization is attempting to shield their home planet from excessive stellar radiation because their star might be entering a brighter phase of its evolution. They might construct a gigantic sun umbrella or a series of massive orbiting screens. While this scenario also explains the presence of large opaque objects, it again suffers from the lack of other detectable techno-signatures and the monumental scale required. These hypotheses are certainly compelling as thought experiments, but they rely solely on the strange light curve itself, offering no other observational confirmation. In science, we adhere to Occam's razor. Entities should not be multiplied unnecessarily. As long as there is any remaining possibility, however remote, of explaining the phenomenon through natural causes, the hypothesis of extraterrestrial intelligence must remain secondary. It is a beautiful, thrilling idea, but it demands far more compelling evidence than just an anomalous dip in brightness. To solve this riddle, astronomers set out to determine whether Tabby's star was truly unique, or if the cosmos held other similar blinking stars. If this was a rare but natural phenomenon, statistically, other examples should exist. This kicked off a massive search for Tabby's star analogues within the datasets of various telescopes. Scientists developed specialized algorithms to sift through the light curves of millions of stars, searching for similar, deep, irregular dips in brightness. They did, in fact, find such stars. There weren't many, only about 24. These objects were unofficially dubbed flashing stars, or dippers. Studying these analogues yielded crucial information. It turned out that the majority of them were young stars still enveloped by protoplanetary disks. Their erratic behavior was explained by the presence of dense clumps of gas and dust within these disks. Crucially, unlike Tabby's star, these objects showed a strong excess of infrared radiation, which betrays the presence of a disk. This reinforced the conclusion that Tabby's star is not a young star. However, the search also uncovered other distinct objects. For instance, the star HPIC 2339 also exhibited irregular dimming, but it was found to be a binary system where one star is circled by a disk that periodically eclipses the second star. Other stars were found whose dimming was caused by the transit of a massive exoplanet sporting a colossal ring system far surpassing that of Saturn. While each discovery was fascinating in its own right, none of the found objects proved to be an exact match for Tabby's star. All of them either displayed the telltale infrared signature, were part of a binary system, or exhibited dimming that wasn't as deep or chaotic. The search for analogues revealed a veritable zoo of mechanisms across the universe capable of causing strange, stellar light variations. But it also underscored the singularity of Tabby's star. It remains one of a kind, an old, solitary star, lacking any sign of a dusty disk, yet demonstrating both rapid, short-term and slow, long-term dimming. This suggests that either we are witnessing an extremely rare event that happens once every few million years, or we still fundamentally misunderstand the physics of stars or their immediate surroundings. The search continues, and perhaps one day, telescope data will reveal its true twin, helping us finally solve this cosmic puzzle. For a long time, one of the biggest gaps in our understanding of Tabby's star was whether it had a companion. Many stellar oddities can be explained by the presence of a second star in the system. The companion's gravitational pull can destabilize the orbits of planets or comets, triggering catastrophic events and generating clouds of dust. Could Tabby's star have a dim satellite that we simply haven't spotted yet? Astronomers launched an exhaustive search. They utilized the most powerful telescopes available, like the Keck Observatory in Hawaii, and employed specialized techniques such as adaptive optics. This technology compensates for atmospheric distortion, allowing them to capture ultra-sharp images, and the search paid off. A faint red dwarf was discovered approximately 885 astronomical units, or AU, from Tabby's star. An astronomical unit is the distance between the Earth and the Sun, meaning this companion is incredibly far away, roughly 20 times farther than Neptune is from our own Sun. This discovery was immensely important. The presence of a companion, even one so distant, could hold the key to the mystery. Its gravity might periodically shake up Tabby's Oort cloud, the hypothetical reservoir of icy bodies located at the far reaches of the system. Such a disturbance could send a flood of comets hurtling toward the central star, lending strong support to the cometary hypothesis. Now that idea had a concrete physical mechanism. However, subsequent research tempered this enthusiasm somewhat. First, the distance between the two stars is vast. For the red dwarf's gravity to significantly impact the inner regions of the Tabby system, its orbit would need to be very specific and highly unusual. Second, calculations demonstrated that even if the companion is responsible for a cometary shower, such events would occur extremely infrequently, perhaps only once every tens or hundreds of thousands of years. We would have to be incredibly lucky to witness such a moment right now. Furthermore, as we recall, the cometary hypothesis still fails to adequately explain the star's observed secular dimming. So, while the discovery of the companion star added an important detail to the overall picture, it wasn't the silver bullet that solved all the problems. It provided a possible mechanism for one of the scenarios, but it didn't make that scenario the only valid one. The mystery remains, but now we know that Tabby's star is not alone in its galactic journey, and its distant satellite may well be the indirect culprit behind the strange events we continue to observe. Let's return once more to the most solid piece of evidence we have. The occulting material is dust. We know this because of the observed stellar reddening. But what if this dust isn't caused by comets or planetary collisions? There's another less obvious source, the star itself. Certain types of stars, especially those late in their evolution, eject material from their surfaces. However, Tabby's star is a main sequence star just like our Sun, and this behavior is highly unusual for its type. But there is a more subtle mechanism. What if Tabby's star possesses a strong magnetic field that interacts with a disk of gas and dust that we cannot see directly? This interaction could create complex structures known as dust traps, where dust particles might accumulate into dense clumps. These clumps orbiting within the disk could then cause the observed dips in brightness. This model is compelling because it can explain the complex, repeating, but non-strictly periodic nature of the dimming events. However, it requires the presence of a disk which remains undetectable in the infrared spectrum. Perhaps the disk consists of extremely cold gas and contains almost no dust except in the specific locations where it is gathered in these traps. Another, even more speculative idea involves so-called rogue or free-floating planets. These are worlds that have been ejected from their home systems and now wander through interstellar space. What if such an orphaned planet, surrounded by a thick cloud of dust and debris, perhaps remnants of its violent expulsion, happened to pass between us and Tabby's star? This event would certainly be extremely rare, but it could potentially account for a single, long, and complex dimming event. Crucially, though, it fails to explain the repeating dips recorded by Kepler, nor does it address the long-term secular dimming. Every new hypothesis, in attempting to solve one problem, inevitably creates another. Perhaps the correct answer isn't a single theory, but a combination of several factors. For instance, a binary companion star triggers a comet shower. The disintegrating comets create a dust cloud, and that dust cloud then interacts with the star's magnetic field. While such a complex multi-component model might explain more of the details, it becomes incredibly difficult to verify. It grows too flexible, allowing it to be fitted to match almost any set of data. Science, however, strives for simple and elegant explanations, and so far that perfect explanation for Tabby's star remains undiscovered. Following the 2017 observations which confirmed the dusty nature of the dimming events, scientists eagerly awaited new activity to study the phenomenon in even greater detail, and Tabby's star didn't keep them waiting long. In 2018 and the subsequent years, several more series of dimming events were recorded. Each new occurrence allowed researchers to refine the properties of this mysterious dust. Observations confirmed that the dimmings were not random. They occurred in groupings or seasons. There were active periods where multiple successive dips in brightness occurred, followed by long stretches of quiet. This suggests that the dust cloud isn't uniform, but instead consists of several individual clumps orbiting together. When this group of clumps passes in front of the star, we observe a season of dimming. Chromatic analysis during these newer events yielded even more intriguing results. It turned out that not all the dust is the same. Some dimmings were caused by clouds of very fine dust, which, as we know, blocks blue light more effectively than red. However, other brightness dips were grey, meaning all colors were blocked almost equally. This indicates that in these instances we are dealing with larger dust particles, possibly several microns in size or more. This discovery further compounded the mystery. Now we must account for at least two different populations of dust, one of very fine particles and another of much larger ones. Where did they come from? Perhaps the fine dust is the result of ice sublimation from comets due to stellar light, while the larger particles are the solid debris left behind after those comets disintegrated. Alternatively, we might be observing different stages of dust cloud evolution. Over time, larger particles collide, fragment, and break down into the fine dust we observe. These new data made the pure cometary hypothesis more compelling, as it can explain the presence of multiple particle types. However, the problem of the secular, long-term dimming has not gone away. None of these new facts provided a simple answer as to why the star has been slowly fading for over a century. The mystery of Tabby's star is like an onion. Peel back one layer, and you find the next one underneath, even more complex. Every new observation answers one question, only to raise two more. Let's take a closer look at the most mysterious aspect of this story, the star's long-term dimming trend. This fact, first discovered by Bradley Schaefer, remains the hardest piece of the puzzle to explain. If this trend is real, it implies that the amount of material blocking the star's light has been constantly increasing for at least a century. Where exactly is this material coming from? One idea suggests that we aren't seeing an accumulation of dust at all, but rather an internal process within the star itself. For instance, the star might be going through some sort of long-term activity cycle, causing its luminosity to slowly drop. However, we don't currently have models that predict this type of behavior for an F-type star. Moreover, spectral analysis shows no anomalies that would indicate unusual processes deep inside its core. But if dust is the culprit, its source must be constant and incredibly productive. Could we be witnessing the slow destruction of an entire planet? If a planet approached the star too closely and entered the so-called Roche limit, the star's powerful tidal forces would begin tearing chunks off of it. This process could continue for a long time, constantly supplying new debris and dust into orbit, but this scenario should be accompanied by strong infrared radiation coming from the heated dust, which we simply don't observe. Yet another hypothesis brings us back to the idea of an interstellar cloud. What if it's not just a simple cloud, but a boundary between two regions of the interstellar medium with differing densities, and Tabby's star is crossing that boundary right now? This explanation sounds elegant, but it requires a huge coincidence. Why is this specific star, which we happen to be watching so closely, situated in such a unique location? More recently, another interesting, albeit speculative, idea has emerged. What if Tabby's star didn't eat a planet, but rather consumed its own companion star sometime in the past? These events, known as stellar mergers, certainly happen in space. A merger results in a single, more massive star surrounded by a disk of ejected material. Over time, that new star can stabilize and the surrounding disk can cool down, eventually becoming invisible in the infrared spectrum. Perhaps the long-term dimming is a slow echo of that ancient catastrophe, while the quick, rapid dips are the result of dense clumps passing within this residual disk. This theory manages to explain many aspects, yet it remains purely speculative. The truth is that as of today, the scientific community has no single agreed-upon explanation for the secular dimming. It remains the biggest gap in our understanding of this astonishing system. It's time to take stock, review the current status, and consolidate everything we know, and crucially, everything we don't know about Tabby's star. What do we know for certain? First, the star exhibits two distinct types of anomalous behavior: rapid, irregular, and very deep dips in brightness, as well as a slow, century-long dimming trend, often called secular dimming. Second, we know that at least the rapid dips are caused by a cloud of dust passing in front of the star. This is confirmed by analyzing the star's color change during these dimming events. Third, we know this dust is composed of varying particle sizes. There is very fine dust that scatters blue light, and there are larger particles that block all colors uniformly. Fourth, we know there is no significant amount of warm dust surrounding the star. This essentially rules out scenarios involving a young protoplanetary disk or a recent planetary collision. Fifth, we know the star has a distant companion, a red dwarf. Now let's turn to what remains unknown. The single most crucial question is, what is the source of this dust? None of the existing hypotheses, whether a swarm of comets, a disintegrating planet, or the aftermath of an ancient stellar merger, can fully and consistently explain all the observed facts. The secular dimming remains especially challenging to explain. We don't know if the dust is orbiting the star, making it circumstellar, or located in the vast interstellar space between the star and us. While most data points toward a circumstellar origin, even this version presents significant difficulties. We lack understanding of the exact geometry and dynamics of the dust cloud. Why does it possess such a complex structure, And why do its dimming events appear to happen in seasons? And of course, we cannot 100% rule out the most exotic hypotheses. While the idea of an alien megastructure seems highly improbable due to the absence of excess heat and radio signals, some scientists urge us not to dismiss it entirely until a convincing natural explanation is found. Tabby's star is a perfect illustration of how science truly works. It is not a collection of ready-made answers, but rather a continuous process of asking questions and gathering evidence. This star has challenged our deeply held assumptions about how stellar systems should behave, forcing us to consider the boldest and most unexpected ideas. The investigation continues. What are the next steps scientists are planning to take to finally solve the mystery of Tabby's star? The key strategy remains continuous monitoring. Thanks to successful crowdfunding campaigns and significant interest from major observatories, the star is now under constant surveillance. Every new dimming event presents an invaluable opportunity to gather more data. Astronomers plan to deploy more advanced instruments to analyze the star's light during these events. High-resolution spectroscopy is particularly crucial. This method, like a prism, splits the star's light into its component colors, allowing us to see dark absorption lines within the spectrum. When a dust cloud passes in front of the star, any associated gas will leave its unique fingerprints in the spectrum. If we detect lines corresponding to water vapor or other volatile compounds, this would be powerful evidence supporting the cometary hypothesis. Conversely, if we find traces of silicates or metals, it would suggest the destruction of a rocky planet or asteroid belt. Another vital direction is polarimetry. Light from a star is typically unpolarized. The electromagnetic waves oscillate in all directions. But when this light scatters off dust particles, it can become partially polarized. By measuring the degree and direction of polarization, researchers can gain significant insights into the shape, size, and orientation of the dust grains, and this will help us build a more accurate model of the mysterious cloud. Naturally, the search for techno-signatures will continue. Although the odds are low, the SETI Institute and other organizations will keep periodically listening in on Tabby's star across the radio and optical spectrums. This is a case where a negative result is still a result, but the hope for a breakthrough discovery of the century always remains. Finally, scientists will continue the search for other stars exhibiting similar behavior. With the launch of new survey telescopes, such as the upcoming Vera C. Rubin Observatory, which will scan the entire sky every few days, we stand a real chance of finding an entire population of these objects. By studying their collective properties, we can determine whether Tabby's star is a unique cosmic anomaly or merely a representative of a new, previously unknown class of astronomical phenomena. The future of this research promises to be truly exciting. Let's indulge in a little bit of speculation and imagine sending an exploratory probe to Tabby's star. Of course, with our current technology, such a journey would take tens of thousands of years, but it makes for a fascinating thought experiment. What would we actually see as we approach this mysterious system? If the cometary hypothesis holds true, the scene would be one of unimaginable scale. We'd witness a gigantic, elongated swarm of thousands of icy chunks, each surrounded by a hazy coma, dragging tails of gas and dust behind them. This swarm would flow along its orbit like a cosmic river. The star itself would be nestled in the densest part of this flow, periodically disappearing behind these passing icebergs. It would be a majestic and chaotic spectacle, a powerful reminder of the raw, primeval force of the cosmos. However, if the planetary catastrophe scenario is correct, the picture would be starkly different, much darker. We would see the star encircled by a ring of debris of every size, from gigantic asteroids, once fragments of a planetary crust, down to the finest dust. It would be a cosmic graveyard, a monument to an ancient tragedy. The orbit would be saturated with colliding fragments, constantly generating new flashes and fresh clouds of dust. But what if, against all odds, the megastructure hypothesis proved true? Upon approaching the system, we might not notice anything at first, but as we got closer, gigantic dark silhouettes would begin to emerge against the star's backdrop. These wouldn't be natural objects. They'd be meticulously engineered constructions of regular geometric shapes, colossal panels, the size of continents, slowly rotating in their orbits to always face the star. Transport flows would dart between them, and somewhere in the shadows of these giants, a civilization would exist, a species that had solved one of the most complex engineering challenges in the entire universe. This final picture is, admittedly, the most unlikely. Yet it is the one that captures our imagination and compels us to gaze repeatedly into that distant point of light. Tabby's star serves as a potent reminder of how little we still know about the universe. It shows us that outside of our comfortable world, phenomena may exist that we cannot yet even begin to comprehend. And that ultimately is the greatest beauty of science, the endless quest for answers to the most profound questions. The saga of Tabby's star is more than just a scientific whodunit. It's a brilliant illustration of how 21st century science has fundamentally changed. In the past, major astronomical discoveries were strictly the domain of professionals working at giant observatories. But now, thanks to technology and the internet, anyone can genuinely contribute. It was citizen scientists, volunteers from the Planet Hunters project, who first flagged the star's bizarre behavior. They weren't professional astronomers. They were regular people, teachers, engineers, and homemakers, using their free time to sift through data, simply looking for something interesting. Their curiosity and sheer attention to detail led to one of the most intriguing discoveries of the last decade. This whole situation demonstrated the incredible power of crowdsourcing in science. The human eye and brain are still uniquely capable of spotting anomalies and patterns that might easily slip past automated algorithms. But the story doesn't end there. When professional astronomers needed funding for further observation, they bypassed traditional government grants. Instead, they appealed directly to the public via Kickstarter. Thousands of people worldwide chipped in their own money, eager to help solve this cosmic riddle. This clearly shows the immense public appetite for fundamental science, especially when it's presented in an exciting and easily digestible format. Tabby's star became a true global unifier. Professional researchers, amateur stargazers, programmers, science fiction writers, and curious people everywhere tracked the news, debating theories on forums and social media, and eagerly sharing ideas. It truly became the people's star. It blurred the line between science and society, proving that profound discoveries result from collective effort. This collaborative spirit may be the most important legacy of this entire mystery, regardless of what the final solution turns out to be. It inspired a new generation to look up at the cosmos and showed that every single one of us can become part of the great adventure called scientific discovery. Let's dive into the psychological side of this whole saga. Why did the enigma of Tabby's star grip our collective imagination so fiercely? Why did the news of the Alien Megastructure star spread across the globe like wildfire? The answer lies in our deeply rooted desire not to be alone in the universe. The idea of other intelligent civilizations has fascinated humanity since ancient times. It shows up in our myths, our legends, and, naturally, in countless works of science fiction. But until recently, we never had a single, real, observable candidate for a potential home of extraterrestrial intelligence. Tabby's star, for a brief moment, gave us that hope. It transformed the abstract question, are we alone in the universe? into a concrete query. What exactly is happening out there in the Cygnus constellation? This wasn't just another blurry photo from Mars or a disputed radio signal. These were solid, verifiable data points gathered by one of the most reliable scientific instruments we possess, and which, at first glance, seemed easiest to explain by intelligent activity. This sparked what we might call a cosmic awe, a powerful cocktail of excitement, curiosity, and a slight fear of the unknown. Even when subsequent data made the alien hypothesis less likely, interest in the star didn't fade. Why? Because this story proved to be far more complex and fascinating than simply, yes, it's aliens, or no, it's not aliens. It evolved into a gripping scientific detective story, where every clue was met with a counter-clue, and every answer only spawned a new mystery. We, the observers, got the chance to follow the scientists' work in real time, their heated debates, their breakthroughs, their disappointments, and their new discoveries. This made science feel alive and inherently human. We saw that scientists don't have all the answers ready-made. They can make mistakes, and they are willing to put forward bold, even near crazy, hypotheses. Tabby's star satisfied our need not just for wonder, but for genuine knowledge. It showed us the sheer beauty of the scientific method and forced us to contemplate our place in the cosmos. And even if the final solution turns out to be some exotic yet entirely natural phenomenon, the journey to find that answer will have been well worth the effort. Let's discuss where Tabby's star fits into the larger context of the search for life in the universe. Traditionally, this search, known as astrobiology, focuses on finding Earth-like planets, specifically those within habitable zones. These are regions around stars where conditions allow for liquid water to exist on a planet's surface. We look for biosignatures, chemical traces in these planets' atmospheres that might indicate life, such as oxygen or methane. Essentially, this is a search for life that resembles our own. The SETI project, on the other hand, searches for technosignatures, narrowband radio signals or laser pulses that might be artificial messages. This is the search for intelligent life that wants to be found. Tabby's star, however, proposed a completely new third path. It forced us to consider searching not for active messages but for traces of a civilization's large-scale activities, a civilization that isn't trying to contact us, but is simply living its life. This approach is often referred to as cosmic archaeology or stellar engineering. Instead of listening for signals, we can start looking for anomalies that simply don't fit natural models. These anomalies aren't limited to Dyson spheres. They include other oddities, unusual chemical compositions in planetary atmospheres that suggest industrial pollution, artificial lighting on the night side of an exoplanet, or even strange transits, just like the one observed around Tabby's star. This third approach significantly expands our possibilities. A civilization might exist for millions of years, yet the period when it actively uses radio communication might be incredibly brief. However, the traces of its engineering efforts, especially if they reach planetary or stellar scales, could persist far longer. Tabby's star, even if it eventually proves to be a natural phenomenon, has already played its role. It became a catalyst for an entirely new direction within SETI. Scientists have begun systematically searching astronomical data for similar anomalies. Projects have been launched, such as the Vanishing and Appearing Sources During a Century of Observations, or VASCO, which aims to find objects that have either appeared or vanished in the sky over the last 7 decades. Perhaps other impossible objects are hidden somewhere in old archives, objects that simply went unnoticed. So thanks to this distant and strange star, our arsenal in the search for intelligent life has become richer and far more diverse. When we discuss Tabby's star, it is crucial to grasp the colossal distances over which this cosmic drama unfolds. The star is located about 1,470 light-years away from us. This means the light we are analyzing today left the star during Earth's early Middle Ages. Everything we observe is essentially a ghost of the past. The dimming events that the Kepler telescope recorded between 2011 and 2013 actually took place back in the 6th century AD. Furthermore, the secular dimming trend, which we noted starting in the late 19th century, would have truly begun sometime in the 5th century. This fact imprints a unique philosophical quality onto the entire story. We are merely passive observers watching a very old film. We cannot influence the events, we cannot pose a question and receive an immediate answer. Even if we were to send a radio message traveling at the speed of light towards Tabby's star, any reply, should one exist, would only reach us 3 millennia later. This vast distance also makes many of the proposed hypotheses even more astounding. Just imagine the sheer scale of an alien megastructure that remains visible from 1,500 light-years away. It would have to be something truly cyclopean, the creation of a civilization that mastered control over the energy output of its own star. The same challenge applies to natural phenomena. A swarm of comets capable of blocking 22% of the star's light must be so immense and dense that it defies imagination. It serves as a stark reminder that in space, scales operate entirely differently than the ones we are accustomed to here on Earth. On the other hand, this immense distance is also the primary source of our uncertainty. We see the star merely as a single point of light. We cannot resolve any details. We cannot visually confirm what is orbiting it. All our information comes solely from fluctuations in its overall brightness. It's akin to trying to understand what is happening in a distant city at night just by observing the flickering of its lights. We can build models and propose hypotheses, but we will always be constrained by a fundamental lack of hard data. Perhaps we will only unlock the final mystery when a new generation of telescopes emerges, ones capable of capturing direct images of circumstellar disks or analyzing starlight with accuracy that is currently unattainable. Until then, Tabby's star will remain for us a beautiful and distant mirage, a symbol both of the cosmos's boundlessness and the current limits of our knowledge. Let's step back from the depths of space and return to Earth to examine how this discovery has permeated our culture. Tabby's star quickly escaped the confines of academic journals and became a genuine pop culture phenomenon. It became a source of inspiration for sci-fi writers, artists, musicians, and video game developers alike. Dozens of stories and novels featuring the mysterious star have been published. In some, it truly is the home of an ancient civilization building Dyson spheres. In others, it serves as the backdrop for cosmic catastrophes or a portal to another dimension. Tabby's star became a convenient and instantly recognizable setting for the boldest science fiction concepts, largely because its actual real-world story sounds like science fiction itself. In the visual arts, paintings and digital works emerged, all attempting to visualize what might be hiding near Tabby's star. Artists depicted giant swarms of comets resembling celestial snakes, crumbling planets, and of course, majestic alien megastructures glittering with lights against the backdrop of their host star. These images helped millions of people better grasp the scale and beauty of the phenomenon. Even music found echoes of this story. Electronic musicians and ambient artists created tracks inspired by the star's mysterious blinking, attempting to translate the feeling of cosmic mystery and solitude into sound. However, this popularity has a downside. The media landscape quickly became flooded with speculation, unverified information, and outright pseudoscience. The image of the alien star proved so powerful that many people still believe the existence of a megastructure has already been proven, completely ignoring all scientific counter-arguments. This highlights the critical importance of separating scientific fact from compelling but unproven hypotheses. It also underscores the immense responsibility borne by scientists and science journalists to present information accurately. Nevertheless, the overall cultural impact of Tabby's star can be assessed as profoundly positive. It awakened an interest in astronomy in millions of people, forcing them to ask fundamental questions about the universe and our place within it. It demonstrated that real cosmic phenomena can be just as astonishing and mysterious as anything we might invent, and that perhaps is its greatest contribution to our shared culture. Let's ask ourselves a crucial question. Could we be missing something similar right here in our own solar system? Of course, we would have noticed an object the size of the one orbiting Tabby's star long ago, but the history of astronomy is filled with examples of us overlooking the obvious, things that were right under our noses. For instance, the asteroid belt between Mars and Jupiter wasn't discovered until the early 19th century. Before that, no one suspected the existence of millions of rocks orbiting the Sun. And the Oort cloud, that hypothetical reservoir of comets on the outermost fringes of the solar system, still hasn't been directly observed. We only know it exists through indirect evidence, the orbits of long-period comets. Perhaps there is something lurking in our own system that we just haven't spotted yet, such as the hypothetical Planet 9 or Planet X. Certain anomalies in the orbits of trans-Neptunian objects strongly suggest that a Neptune-sized planet could be hiding far beyond Pluto. The search for it has been going on for years, but so far without success. If this planet exists, its gravitational influence on Oort cloud comets might, in the past or the future, trigger comet showers similar to what we may be seeing around Tabby's star. The story of Tabby's star teaches us to pay close attention to anomalies. Sometimes the most important discoveries aren't hidden in data that confirms existing theories, but in the data that strongly contradicts them. These are what we call paradigm-shifting anomalies. When astronomers in the 19th century noticed that Uranus's orbit slightly deviated from predictions, they didn't dismiss the data as an error. Instead, they hypothesized that another planet existed beyond Uranus and calculated its exact location. That's how Neptune was discovered. Tabby's star is an anomaly of the same type, only on a far grander scale. It simply doesn't fit into our current understanding of stellar evolution and planetary system dynamics, and that is a good thing. It means our knowledge is incomplete, and we still have much to uncover. Perhaps solving the mystery of Tabby's star will lead to the discovery of a new physical law or an entirely new type of astronomical object. That discovery, in turn, will help us better understand our own solar system and the billions of other systems throughout our galaxy. When we talk about Tabby's star, we often use the word unique, but how unique is it really? Statistically, the Milky Way holds hundreds of billions of stars. Even if the phenomenon we are observing occurs in only one star out of a million, or even one out of a billion, there should still be thousands or even hundreds of thousands of such objects throughout the galaxy. So why have we only found one? The answer might simply be that we haven't been looking hard enough. The Kepler telescope observed only a tiny patch of sky, roughly 1/400th of the entire celestial sphere. Its field of view contained only about 150,000 stars. Finding just one strange object among them was already incredibly lucky. It's possible that if we could conduct the same detailed long-term monitoring of all the stars in the sky, we would find many sisters to Tabby's star. Another explanation might lie in the temporal factor. Perhaps the phase Tabby's star is currently experiencing is extremely brief by astronomical standards, lasting, say, only a few thousand years. A star exists for billions of years, and catching it during this short but turbulent period is a massive stroke of luck. If that's the case, there could be many such stars in the galaxy at any given moment, but they flicker on and flicker off at different times. We might have just been lucky enough to catch this one in its active phase. It's like watching a field of fireflies at night. Only a small fraction of them are illuminated at any instant, even though the total population might be enormous. This consideration gives us hope. With the launch of new and upcoming all-sky survey missions, such as the TESS satellite or the already mentioned Vera C. Rubin Observatory, we will significantly increase our chances of discovering similar objects. These projects will monitor millions of stars across the entire sky. If we find even a few dozen of these blinking stars, we can begin studying them as a class of objects. We will be able to compare their properties, age, mass, companion stars, and the type of dimming they exhibit. And then perhaps the overall picture will start to clarify. We will understand what is common to all of them and what is unique to each individual star. The mystery of Tabby's star will then cease to be the enigma of a single object and instead become the key to understanding an entirely new class of phenomena in the universe. Let's circle back to the very first hypothesis published by Tabitha Boyajian's team, the idea of a massive comet swarm. Despite the complexities it introduces, it still ranks as one of the leading explanations. Let's try to visualize exactly how this mechanism might work in light of the new observational data. We have Tabby's star and its distant companion, a red dwarf. Imagine this companion's orbit is extremely eccentric. Once every few tens of thousands of years, it sweeps close to Tabby's star's Oort cloud. The resulting gravitational disturbance dislodges millions of comets from their orbits, sending them cascading into the inner system. Crucially, they don't move as a single lump, but form a long, highly elongated stream. What we are observing now is the passage of the densest central portion of this stream. This neatly explains why the dimming event is occurring precisely during our era. Different clusters of comets within this flow might travel along slightly different trajectories, which could account for the observed seasons of dimming. When an especially dense clump composed of numerous large comets passes in front of the star, we observe a dramatic, deep plunge in brightness. Conversely, when we look through a more sparse section of the stream, made up primarily of fine dust formed by ice sublimation, we register much shallower dimming events. The presence of particles of different sizes, or grey versus red dust, also fits well into this model. Large intact comet fragments cause the grey dimming effect, while clouds of fine dust, stripped from their surfaces by stellar wind, are responsible for the red observations. But what about the secular dimming, the continuous long-term drop in brightness? This is arguably the trickiest aspect. It's possible that the leading edge of this massive comet stream has already passed through the system and dispersed, creating an extremely diffuse yet enormous cloud of dust that now slowly encircles the star. As a result, we, along with the star, are gradually entering this pervasive cloud, which creates the effect of a slow, continuous decrease in overall brightness. This model is undoubtedly complex. It requires a great number of coincidences and precise cosmic alignments. However, unlike many competing ideas, it is capable of explaining, at least qualitatively, almost all observed facts using only established laws of physics. It demands neither aliens nor new physics. It merely asks us to accept that sometimes space hosts events that are incredibly rare, immensely chaotic, and truly massive in scale. And we may be lucky enough to be witnessing one right now. The entire saga surrounding Tabby's star brings up a fascinating philosophical question. What are we actually looking for when we gaze out into the cosmos? Are we seeking confirmation of our existing theories? Are we simply searching for new worlds similar to our own? Or are we hunting for something radically different, something that will challenge our understanding and force us to reconsider everything we thought we knew? Tabby's star falls squarely into that last category. It is astronomy's true black swan. This term, coined by the philosopher Nassim Taleb, refers to an event that is utterly unexpected, carries massive consequences, and which people subsequently try to rationalize after the fact, making it seem predictable in hindsight. The discovery of Tabby's star was completely unforeseen. Nobody predicted the existence of objects like this. Its ramifications for science have been enormous. It has spawned dozens of new research papers, forced us to rethink anomaly detection methods, and even opened up a new avenue within SETI. We are now squarely in the third stage, trying desperately to find a rational explanation for it, hoping to fit it neatly back into our current worldview. These black swans are the true engines of scientific progress. They prevent science from becoming rigid and trapped in dogma. They are vital reminders that the universe is far richer, more complex and stranger than even our wildest models suggest. Copernicus, Galileo, Newton, Einstein, each of them in their time confronted anomalies that simply refused to fit the prevailing consensus. Their attempts to explain those anomalies sparked scientific revolutions. We don't know if unlocking the mystery of Tabby's star will lead to a new revolution in astrophysics. Perhaps the ultimate explanation will prove to be mundane, but the search itself, the very necessity of thinking outside the box and breaking free from established models, is an invaluable experience for the scientific community. This star teaches us humility in the face of the cosmos. It demonstrates that even after centuries of astronomical observation, we can still encounter phenomena that leave us completely dumbfounded, and that is a beautiful thing, because as long as the universe holds secrets, humanity will have the motivation for discovery, for moving onward and upward toward the stars. Tabby's star is more than just an object. It is a profound challenge issued by the cosmos itself. And the way we choose to answer that challenge says everything about who we are. So our long journey to the most enigmatic star in the known universe is coming to a close. We began with a simple, yet strange graph, first spotted by the keen eyes of amateur enthusiasts. We explored the mind-boggling hypothesis of an alien megastructure, which for a brief moment made us all believe in a miracle. We weighed and discarded one natural theory after another, everything from protoplanetary disks to planetary collisions. We delved into the chaos of a gigantic comet swarm and wandered through clouds of interstellar dust. Every new observation seemed only to deepen the mystery, adding a slow, century-long dimming trend to the already baffling rapid dips. Today, the most likely culprit appears to be dust, possibly of cometary origin, orbiting in a very unusual path. But even this is just the most plausible of several unproven hypotheses. None of these theories can definitively explain all of the star's strange behaviors. And that is its ultimate value. Tabby's star is the perfect scientific enigma. It remains unsolved, forcing scientists to invent new methods of observation, rethink old theories, and, most importantly, continue looking up at the sky with wonder and curiosity. It has shown us that the universe is still full of surprises, and the most incredible discoveries might be waiting where we least expect them. Thank you for spending this time with me, pondering this cosmic puzzle. I hope this lecture helps you drift off into a calm and deep sleep, filled with dreams of distant worlds. And before you fall asleep, I have a question for you. What do you think is hiding around Tabby's star? an alien megastructure, a giant dust cloud, or perhaps something we cannot even yet imagine? Share your boldest theory in the comments below. I'd love to read them. Don't forget to subscribe and hit that like button if you enjoyed our journey. Good night.